Hi, everyone. Welcome and thank you for joining us for AstroTours. My name is Simran Nerval, and I'm a PhD student here at the University of Toronto. I would like to begin today's event with a land acknowledgement. I'm tuning in from Toronto, which is situated on the traditional land of the Huron-Wendat, the Seneca, and most recently the Mississaugas of the Credit River. This territory was subject to the Dish with One Spoon, One Palm Belt Covenant, an agreement between the Iroquois Confederacy and the Confederacy of the Ojibwe and Allied Nations to peacefully share and care for the resources around the Great Lakes. Today, this meeting place is still home to many Indigenous peoples from across Turtle Island, and I'm grateful to have the opportunity to work on this land. Acknowledging the traditional territory in which we live and work is a small but important step that reminds us to learn more about the Indigenous peoples in these regions, to consider the history and ongoing colonialism on this land, and to reflect on how each of us can contribute to reconciliation. We're lucky enough today to have people tuning in from across the country. You can visit native-land and whos.land to learn about the land that you're on and who it belongs to. So if this is your first time attending AstroTours, we generally run our tours on the first Thursdays of most months. And this month we have our lecture by Fergus Horrobin. After the talk, we'll head over to a Zoom room for a variety of activities. So for example, we're going to have a virtual tour of ALMA and then also an Ask an Astronomer room. And after the event, please fill out our feedback form at bit.ly/astrotours. AstroTours is organized and run by graduate students in the Department of Astronomy and Astrophysics at the University of Toronto. We do this to share our passion, and we really value your feedback from our attendees. And also remember during the talk to put your questions for Fergus into our YouTube chat. Before we get into tonight's event, I will just highlight some upcoming events. So next month in June, we're going to have a lecture by Anna O'Grady about how her search for a rare class of stars and how it led to an unexpected twist. We're also going to have our activities themed for Pride Month. And this will be on Thursday, June 2nd at 8 p.m. EST, and the location is to be determined. Also, make sure to check out the Cosmo from Your Couch series. You can get more information about that on the Dunlap Institute Facebook page and YouTube channel. Also, you can see a variety of online events being held this month by the Royal Astronomical Society of Canada, and you can visit their website for more information. So now on to tonight's speaker. Fergus is a third-year PhD candidate at the University of Toronto's Department of Astronomy and Astrophysics and the Canadian Institute for Theoretical Astrophysics. He uses fluid dynamic simulations of protostellar disks, the disks of gas and dust which form around young stars, to understand the formation of planets and the dynamics of young planetary systems. Outside of work, he enjoys spending time outside, particularly cycling and rock climbing. So I'll now pass it off to Fergus to tell us about the birth of planetary systems, from star formation to the solar system.
Okay, great. Thank you so much for that introduction, Simran. So yeah, I'm so excited to be here today to share some of the work that I do, as well as a lot of work that other people have done in this field, trying to connect a lot of the observations that we're making with new state-of-the-art land and space telescopes with the theory that people like me are doing to understand how stars form, how planets form, and how planetary systems evolve, starting from systems around young stars right up to something like the solar system today. So let's start off by talking a bit about some of the motivations for why we want to think about planet formation and things that we can learn already just from the solar system. So one thing is, if you've ever thought about the solar system planets, there's already a couple interesting features of the solar system that might motivate us asking questions about whether these are just random or whether these features could be give us insights into how planet formation actually happened. For instance, if you look at the planets in the solar system and group them in order from the sun to further away, you'll see that the closest foremost planets, which are the small rocky planets, are all inside and closer to the sun relative to the larger planets or the gas giants. And so this asks the question of whether, is there something from planet formation or the way that planets form that sets where small rocky planets are compared to where giant gas-like planets are? Also, if you've ever thought about how the plane of the solar system looks, most of the planets, and I've included Pluto here to show that it's a little bit of an outlier, but most of the planets lie almost exactly in the same plane. And even Pluto, being a little bit out of the plane, is only out by about 17 degrees. So this also gives us a hint that there's probably something interesting that happens that leads to everything being in a plane rather than just being distributed randomly at different heights. And then also to talk about some motivations for understanding planet formation, even beyond what we can learn from the solar system. Over the past few decades, we've had a large number of observations of exoplanetary systems or planetary systems around stars other than the sun. And some of these have proved to be really weird and interesting and confusing planetary systems, very different than the solar system. One of these, TRAPPIST-1, shown here compared to the solar system, has all of the planets incredibly close to the star compared to those in the solar system with proximity to the sun. In fact, here it's showing that even to see what the orbits of the planets look like, we've had to enlarge this image of TRAPPIST-1 25 times relative to our projection of the solar system in order to show all of these planets. And this isn't the only system like this. There's been a whole bunch of these, what we call compact planetary systems, where all of the planets are really close to the star. And this actually brings up some challenges compared to planet formation theories that were proposed before we had observed systems like this. Additionally, another type of planetary system or planet that we've observed that's been rather confusing is something that we sometimes refer to as hot Jupiters. So here I'm showing on the bottom just a little schematic of Mars, Venus, and Earth in the solar system relative to the sun, as well as two planets in a planetary system called Kepler-56. This isn't all exactly to scale, but it's generally showing that in Kepler-56, there's two very large planets, likely Jupiter-sized planets, that are both closer to the star than Mercury is to the sun. And this is another thing that, based on how we think the solar system formed, just shouldn't be possible. So I'm going to talk about how some of the stuff we've looked at planet formation theory has changed over time, and some ideas we have to explain systems like these. So just to give you a brief overview of what I want to talk about, I'm going to break it down into trying to answer a few main questions. And broadly, those questions are, we want to talk about how stars form, and then we want to talk about how planets form, as well as when planets form. Then we're going to answer some of those questions I've raised already, like why are all the solar system planets in the same plane? And how do really different planets like Earth and Jupiter form in the same system? And finally, we're going to discuss this in the context of the solar system versus other planetary systems to answer the question of whether all planetary systems are similar to the solar system or not. So let's start off by talking about star formation. So early on, before stars are forming, we have a region of dense, cold gas and dust that we'd refer to as a nebula, or in the most massive case, a giant molecular cloud. And these nebulas or clouds will continue to cool. So they were heated up during the formation of the galaxy, but now there's nothing heating them anymore. And they're going to cool. And as they cool, the gas is going to contract. It's going to start pulling itself together through gravity. And as it pulls itself together, it's going to become a much more messy flow of gas, kind of like what you might see in a creek that travels over a bed of rocks. And due to this messiness in the flow of the gas and dust is going to start fragmenting and coming into clumps. And some of these clumps are going to have enough mass in them that they're going to become gravitationally connected. The material in it is going to become gravitationally bound to itself, and it's going to collapse down into a star. And to see this, we can look at an example of a simulation of star formation where they started with an idealized cloud of gas, and they actually let this evolve under realistic conditions for the cooling and the gravity of the gas. And you see that there's these clumps forming, and then where these white dots are, that's where they believe that stars may be forming. Then as these stars form, they start giving off light in the way the sun does today. And early on, these stars can give off a lot of light as they form. And that's what you're seeing these jets being thrown out are. This is energy from the stars as they turn on, pushing the gas away. And so early on, we can actually take pictures of this in process. And so this is a picture from the Hubble Space Telescope of a region where young stars are forming. And we can see at the center, there's a very bright area where the star is and bright gas around it, where the light from the star is illuminating and pushing on that gas, heating it up. And then all around it, there's more gas, some of which will end up infalling onto the star as well, and some of which will be pushed away by this force from the light coming out of the star. So then let's talk about what happens to that extra gas around the star. So as we saw in the previous picture, we start out with a whole bunch of gas just kind of distributed evenly in all directions around the star. But then that gas isn't there today. We know that in the solar system, there's essentially none of this gas left in the nearby regions of the solar system. And that's because this gas either gets pushed out by the light pushing on it. So the star is so bright and pushes so that the pressure of the light hitting the gas pushes it out so much that it pushes most of this away and it just disappears. But some of it gets pulled in and captured by the star through gravity. And because it's moving initially, it doesn't actually fall fully onto the star, but it ends up in a spinning disk of gas and dust around the star. And this is the disk out of which planets form. But let's first address the question a little bit more of why this becomes a disk and not just a ball of gas floating around, because this being a disk is going to be important for the structure that we see in planetary systems. So as this gas collapses, if we take a point on the gas, for example, at the non-arrowhead end of this arrow, there's going to be a force that I represent by this arrow of the star's gravity pulling on it. But because it's moving in a circle relative to the star, well, we can also break this force down into two components. There's some of the force pulling it directly towards the star, and the force is simultaneously pulling it downwards towards the center of the disk. Then, because this thing is moving relative to the star, it wants to move away. And you can think about this compared to, say, when you're driving your car and you turn the corner, it feels like you want to keep going the direction the car was before, and like the car is pushing you through the corner. This is the same effect here, as the gas is trying to keep going the direction it was and is simultaneously being pulled towards the star. And so it ends up being in a balance where it ends up in orbit around the star. But then we might think that this part of the gravity pulling it down would just make this thing really thin, and it almost does. But these disks do have some height. And this is because these disks are made of mainly gas. And whenever you try and press a gas together, eventually the gas is going to push back so much that you can't compress it anymore. So the force from pressure pushing back on this gas is going to overcome the force of gravity, and it's going to reach a balance where this disk is relatively thin, but not razor thin. Now, just to show a cool example of this same effect in the solar system, if you don't have gas in the disk, there is none of that pressure support. So in fact, the material in the disk can actually collapse all the way to something razor thin. And this is the case with Saturn's rings, which is really the closest example to us of something that looks like one of these disks, with the main difference between it and these protostellar disks being that Saturn's rings do not have any gas in them. They're just dust. Otherwise, though, they share a lot of similarities. So then another thing that we might wonder is, can we actually observe these disks? So I've told you that we've observed planetary systems, systems of already formed planets. But if we want to learn about how the systems are forming, we would actually like to observe these disks directly. In modern instrumentation over the past couple decades has really allowed us to be able to get a great and large set of images of a whole bunch of these disks. So some of the notable instruments that have done this are the SPHERE instrument at the Very Large Telescope, which is, the Very Large Telescope is just a big lens-based, a big telescope that collects a lot of light. It's land-based, And SPHERE uses adaptive optics to focus the light that's coming in incredibly well, despite the noise introduced from the atmosphere. Because as you might know, if you look through the air, especially when it's hot out, things seem to kind of wobble. So the Very Large Telescope and SPHERE instrument are able to get really precise images despite the fact that they're looking through the atmosphere. Another one that's been used a lot, but sadly is decommissioned now, is the Spitzer Space Telescope. For 15 years, the Spitzer Space Telescope looked at young forming stars to try and look at these processes that are important for star formation, planetary system formation, as well as do spectroscopy of planets themselves. And we've learned a lot about what these disks look like, as well as the chemistry of these disks from Spitzer. And then there's also the Atacama Large Millimeter Array, or ALMA, which you can find out more about after this talk. And this is a large array of radio telescopes in Chile. And it's the largest land-based telescope to do such observations. So it uses an array of radio telescopes spaced over a large chunk of land to get an effectively huge-sized lens to look at these things with. So next, I just want to quickly show you a picture of the electromagnetic spectrum, which some of you might have seen in a science class before, to kind of tell you what type of light we're actually looking at when we observe these disks. So if you've seen this before, essentially we can arrange all the different types of radiation, as we might refer to them, by how long the wavelength is. And those range from things with really small wavelengths or high energy, like cosmic rays and gamma rays, to things like radio waves that have really long wavelengths and relatively low energy. And right in the middle of this, we have the small band of light that we can actually see with the naked eye. However, these disks don't actually emit a lot of light in the range that we can see. Most of the light they can emit is actually in the infrared, a little bit outside of the range of what we can see for things that look red. So the really cool thing here is that all three of those telescopes that I showed before are actually very optimized to look at things not in the type of light that we see, but in the infrared light that we can't see. And they can actually see features and see these disks and create images for us of these disks that we would not be able to see ourselves, even if we were right there. And so just to give you an idea of, well, where this light is coming from, since I said that this gas that collapsed was cold, you might ask, why is it emitting any light at all? Well, when it forms this disk, because the disk is thin, the disk is actually thin enough that the light from the sun can pass and hit the whole top section of the disk. The disk has a lot of dust in it, and because of this, like you might see if, say, you're in a dust storm, the sun doesn't seem to shine as bright. Well, the star also can't shine very deeply into the disk here. But because of the geometry of the disk, a lot of the sunlight's able to hit the surface of the disk and heat the disk far away from the star. And then because the disk is heated by the starlight, well, if you've ever looked at a hot object with a thermal camera or seen a picture of someone looking at a hot object with a thermal camera, they're essentially doing what these telescopes do. So thermal cameras just look at light coming off of objects in wavelengths we can't see, like the infrared light. And so these telescopes are actually going to see this light from the hot dust, the dust that's been heated by the starlight, by absorbing the starlight, which is then re-emitting some of its light into the disk, which just heats the disk. But some of this light goes away into space, and that's the arrows pointing up there. And if we're looking in the direction of this, we can see that emission by using the right type of telescope. And we've seen lots of these disks, but I just want to give you a sample of what some of these look like. So this is a particular sample of about 20 of these disks from observations done with the SPHERE instrument on the Very Large Telescope. And if you look at these, you'll notice that though they all kind of have the same shape that I've been describing, they have a variety of different features in them. Some of these disks are very smooth. Some of these disks have very defined rings. Some of them have many rings versus some of them have one ring. And some of them even have these other patterns like spirals in them. And so one of the big questions that we want to ask when we look at these disks, and one of the big things that theorists in this area have been working on, is given that an observer gives me an image of this disk, how can I tell where these features in it are coming from? And to give you some ideas of things that we think could cause these features, well, one of the big things that, especially early on, we were really excited about causing these features was planets. When a planet's embedded in the disk, so when a planet's forming in the disk and gets big enough, the gravity of the planet starts to pull a lot of material onto the planet, which means that you get rid of material nearby to it. The motion of the planet also drives these waves in the disk, kind of in the same way as how when you drop a rock into a pond, you get waves emanating away from it. And so in several ways, planets can form wave-like, ring-like, spiral-like, as well as gap-like features. So it has actually been shown in many different simulations that we can actually form a whole bunch of these just by putting planets in the right spot. And so early on, this was really exciting because this was essentially the only way we thought we could form these features. And that would mean that we have all these observations of forming planets. Except that's not the whole story, because later on, people did realize that there's other ways that you can form these. So the image on the right is of a simulation where you're getting features in the disk, but there's no planet actually forming. Dust is just clumping together a little bit because of a bump put into the disk. We don't know if these bumps could really happen, but it's believable that, say, starlight could pass a little bit better in one direction than another, heat the disk a little bit more somewhere. And if that happened, it could potentially lead to dust getting more trapped in one area. And people have shown that when you trap more dust in one area, you can get features that look really similar to this. So as of yet, the question hasn't been answered for sure where these features are coming from. But we do know that, but we hope that as we get more detailed simulations and a better understanding of the theory behind this, as well as with next generation instruments, for example, the James Webb Space Telescope, that's another infrared telescope that's going to look with even higher resolution at some of these disks, that we can start to even more and more understand which of these features come from which mechanism, because there are potentially some telltale signs. We just haven't fully uncovered how to see them yet. But so we talked about how one of the sources could be a forming planet. Next, I want to talk about different ways that planets can actually form in these disks. So the kind of most common way that we'd imagine planets forming in this disk, and this is a mechanism that works for forming planets essentially at all distances from the star, and for planets of any size, so this could be an Earth-like planet or a Jupiter-sized planet, is that we imagine we start out with some dust and some gas, and that the dust starts to clump together. And how exactly the dust starts to clump together, we're not fully sure about yet. And this is one of the questions that I'll come back to later, something we still need to answer. But we can make the dust clump together in simulations if we want to. And so when we try and make the dust clump together, and this is showing a simulation of dust clumping as a function of changing the time of the simulation from left to right, you can see that the dust clumps more and more, and eventually at the end state, you get a whole bunch of quite dense regions, which are represented by these circle things. And if you get enough mass into those, they could start pulling each other together gravitationally and clumping more and more. And you could eventually turn all of these kind of boulders that formed out of the dust into planets by just hitting them together and sticking more and more material on. And this is the core accretion model of planet formation. Now, to form a Jupiter-sized planet out of this, you need a little bit more though. After you form this core of rock and out of the dust, Jupiter still has a lot of gas. In fact, most of its mass is gas. So the idea here is that you form this core really fast before the gas disk goes away. And then the mass of that rocky thing, which we estimate for Jupiter would have to be about 10 times the mass of the Earth, pulls gas onto it and captures gas out of the disk, forming a planet like Jupiter. And this works fairly well, but there is a timing problem in some cases with this. See, these disks only survive for about 10 million years before all the gas gets pushed away by the light from the star pushing on it gradually over time. So for this to work to form a Jupiter, we'd have to believe that we could form a 10 Earth mass core on a timescale much faster than 10 billion years to still have ample time to bring gas onto it before the gas is gone. And we're not completely sure if that works or not. And in particular, if we believe it works for Jupiter, we're very much not convinced that this would work for something like the hot Jupiter system in Kepler 56 that I showed earlier. So with observations like that in mind, we will need to think about this a little bit more. Another potential mechanism for forming large gaseous planets, and this one really only works for large gaseous planets because it's going to depend on the gas and dust collapsing together, as this video will show. So you start out with a disk that breaks up into pieces, and in the same way that the star formed out of material collapsing out of the nebula, planets shown by the black dots appearing could potentially form directly by material collapsing from the disk. If this is the case, however, it's going to require that these planets have a significant amount of gas on them, since we know that the mass of gas in these disks far exceeds the mass of dust. So this would really be applicable to Jupiter-like planets. So a moment ago, I mentioned that one thing that we found puzzling is these hot Jupiters, and that both models of planet formation are actually going to end up being difficult to explain them by. And the main reason for this is that in the planetary disk, there's this region that we refer to as the snow line. And essentially, earlier I showed you how the disk is heated by the star. Well, when you get far enough away from the star, you're not heating it enough anymore that you can melt things like ice, water ice, and ice from other things such as methane. So outside this ice line, we have a lot of extra solid material coming from these ices. And this could be incredibly helpful to just having enough mass to form a 10 Earth mass core in the core accretion model, or to make this disk collapse in the direct collapse model. However, in the inner regions of these disks, and certainly in where these hot Jupiter planets are in Kepler 56, it's well inside the snow line. And so there's way less material to form things out of. And it's very puzzling how those planets would get there. So the snowline argument worked very well for the solar system, because effectively the giant planets in the solar system are all found outside where we predict the solar system snowline to be, and the small planets are inside. So this nicely gives an explanation for why our planets are ordered that way. But for these compact exoplanetary systems, we need to look a little deeper and try and understand how we could get a Jupiter planet there without completely throwing out our models for how these protostellar disks work. And just to kind of reiterate this by showing all the observations of planets, at least as of when this paper was published in 2021. So on this plot, I'm showing as dots all the planets that had been observed, and the colors just showing how they were observed. And I put a vertical and an horizontal line at the distance where the Earth is, which is shown on the x-axis. And then on the y-axis, it's showing the mass of the planets in Jupiter masses. And then so the cross I put on in black is showing where Earth would be found on that. And you can also see the other solar system objects, which are all these gray objects in the lower right-hand side. And you can see that there's a lot of things here that look roughly close to the solar system. But that hot Jupiter I showed, it wasn't just two anomalous planets. There's a whole population of them up in the upper left. And then also there's these rocky planets at very small distances. I'll note that the axes on this plot are in logarithmic scale, which means that each of these ticks changes either the distance or the mass by a factor of 10. So there's these rocky planets that are 10 or 100 times closer to their host star than the Earth is to the sun. And some of those are in systems where there's many of them. So forming either many rocky planets close in or even one hot Jupiter close in, we just don't think we have enough material. So one way that we think we might be able to do this, and this is something that I work on a lot these days, is thinking about whether interactions between the planet and the disk as the planet forms could actually pull the planets inward. And this is what we call planet migration. So we can set up these fluid dynamic simulations where we grow a planet in a disk, and then we let the disk, as it generates these features in it, because these features could be asymmetric, the disk can pull gravitationally on the planet, and the pull might not balance. The pull might end up pulling the planet in or out. And it turns out that for realistic setups for these disks, we can actually make planets move inward, and we can potentially make them move inward fast enough that we could start a planet forming where Jupiter is today. And under the right conditions, we could move it in 10 or even 100 times closer than it is if it forms early on while the disk is still there. We've also shown that when we have a whole bunch of small planets, if one of them starts moving inward, the pull of that one planet on its companions can actually help to move the whole system inward. And there's a whole bunch of really rigorous work on this done for TRAPPIST-1 in particular that shows that it's quite likely that these planets started out closer and more tightly spaced than in the solar system, but probably migrated into their end state today. And if we believe these stories, this actually can completely solve our mass deficit problems and allow our planet formation theories for the solar system to be compatible in general for these planetary systems we've observed. Now, to kind of give you some insight into kind of some of the most exciting observations that we have coming recently, I want to point out that the observations of the disks I showed before were like pretty smeared out and relatively low resolution looking. We could see these features, but only on large scales. When I show you this simulation on the left of this planet interacting with its protoplanetary disk, you can see that the features near the planet are much smaller in scale than the types of things we were seeing in the observations from SPHERE that I was showing you before from these large surveys. Well, recently in 2020, SPHERE did a specific survey on a particular system of interest, AB Aurigae, where we believed from other observations that there was a massive planet forming. And I'll note that this is on very large scale. The distance from the star to this planet is about where Neptune is in the solar system, or even a bit further away. But using SPHERE's advanced capabilities, a lot of observing time, and specifically targeting this system, as well as then creating a really detailed pipeline to denoise the image as much as possible, they were able to create one of the best observations of a disk that we believe is forming a planet done to date. And then on the bottom right, I'm showing a zoom in on this where they've also false colored it so that the areas that are bright or hotter in the image on the left are now shown in blue, just to help emphasize them. And you can see that the first one on the left of those two panels is just the false color image of the original image. But then if we zoom in on it into the inner region, so into a box about 2 or 3 times the size of Neptune's orbit, we can see this spiral pattern that when drawn over top and when looked at carefully, actually has a decent amount of resemblance to the type of spiral patterns we see in fluid dynamic simulations of forming giant planets. And there's been a handful of other such observations that similarly have looked really closely at these disks that we believe may be perfect environments to form a planet, and where we've also seen patterns like this. So it's really exciting that with the kind of state-of-the-art technology we have today, as well as next generation technology like James Webb, that we're potentially actually going to be able to start looking at planet formation directly rather than inferring it from large-scale features in the disk. From the perspective of my work, I would also hope that we can allot enough telescope time to look at some of these things for potentially a good chunk of an orbit around their star. And we can actually potentially then try and constrain how these things are moving and actually connect these to the migration models and theories that we have for how planets interact with the disk. As well as we survey more of these systems, we might just get lucky enough to see a system young enough where we're seeing these planets forming right at the beginning and get a much better sense of what the mechanism of planet formation is. So this is really exciting. So then just to finish up, I've talked a lot about what we've known so far and some of the exciting things to come, but I want to talk a little more about some of the questions that have still not been answered that we need to think about, and then talk about whether we think we can answer these anytime soon. So one thing that we'd like to know, and that hopefully these new observations, when done en masse, will be able to help tell us, is how much of planet formation happens during the life of the disk versus after. As in, did the solar system pretty much form during that first 10 million years when the disk was around? Or did a whole bunch of small rocky things and other things, did a whole bunch of smaller planets form and then collide together later to form the planets that are there today? Also, were the planets in their final position when the gas disk left? Or did they move significantly in the billions of years since then? And these are questions that combining observations of exoplanetary systems, particularly young ones, with observations of these disks are hopefully going to try and answer. A big question that we've tried to address with laboratory experiments and simulations, and that hopefully we'll be able to get at soon as our computing resources improve to do these simulations, is how do we actually stick small dust grains together? Because if you've ever played with sand, you know that if you throw sand together, it generally doesn't stick very well. And that's essentially the problem we have in these disks. When we get things that are pretty big, like the size of large asteroids, they start pulling on each other gravitationally, and we can believe that gravity holds them together. But we know that this dust starts out quite small because we have observations of this dust pre-star formation, and we know roughly the size distribution. And the majority of this dust is millimeter or smaller. And so we really need to know how we get this stuff to stick together. And sometimes people refer to this as the 1 meter barrier, because if we can figure out how to grow dust from micron to millimeter size up to 1 meter size, then we're in business to hopefully form planets in a realistic way. Now, one thing that I work on, and so I mentioned planet formation works to form these planets, but unfortunately right now, it mostly only works if we stop it artificially when we know it had to stop. We don't have a good consistent mechanism to stop a planet migrating and to stop it from just slamming into the host star. Likely the case is that we're just not understanding the physics of these disks at the inner edges where we haven't observed them yet, and where simulations are hard because of the intertwined many different types of physics, as well as small scale behavior that happens there. But until we can answer this question, we can't definitely say that planet migration works to create these hot Jupiters or compact planetary systems. And finally, if we're interested in how we get a planet like the Earth with an atmosphere and surface composition that led to life being able to form, we'd ultimately like to know, and we can hopefully learn this by doing chemistry on young forming planets through spectroscopy, as well as on the disks themselves, whether the composition of the surface and atmospheric material is set early during formation, as in when the disk is still there, or whether this is something that happens later on. So hopefully that leaves you with some interesting questions to think about. And now I'm happy to take questions from the audience. Thank you.
Thank you very much, Fergus, for that super interesting talk. So yeah, make sure to put your questions in the Zoom chat for Fergus. So we'll start off with this one. What does it mean to do spectroscopy? You said that you want to do it for like, the planets and the disks. Like, what does that mean exactly?
Okay, great. Yeah, so some of these instruments, I'll go back to the pictures of the instruments. So in particular, the sphere instrument, it has the ability to look at things and take pictures like the ones I showed on the next slide. Like it has the ability to take pictures of the disks like I was showing, but we can also look at the material. We can look at essentially, well, we talked about this electromagnetic spectrum. You can look at how light is being emitted in specific wavelengths on that. So we can look at light that's being emitted in a very specific band, not just infrared in general, but a specific section of the infrared. And we can associate that with known emission frequencies we have laboratory information for a whole bunch of different molecules. We can associate these observations of specific bands of light with laboratory measurements for specific molecules. And then if they look similar, we can say that maybe that chemical element is present in the thing that we're observing. And so that's the big picture idea of what we're doing. And we know roughly what chemicals we're looking for. So we look for certain signatures of things that we'd like to be there to try and learn about it. In particular, we'd like to look for things containing oxygen and carbon because we'd like to know if systems in general have those to form life like us or not.
Yeah, that's super interesting. Another question is, because you were talking about Saturn's rings and how they're kind of like these disks. Does that mean that Saturn's rings can form planets too?
That's a really good question. So some of you might know that Saturn has a lot of moons, many, many more than the Earth and Mars and other small planets do. It has tens of moons, depending on what size of object you would count as a moon. And so the formation of these moons is actually very similar to the formation of planets, or at least that's what we believe. So effectively, this disk around Saturn, in the same way that the disk around the sun allowed the planets to form, the disk around Saturn, some of the material in it formed into these moons, some of which are quite large, being almost the size of planets. And so it is actually really interesting that Saturn's rings are an area that we can actually study how planet formation happens much closer to us than looking at nearby stars.
Just a quick follow-up before we move on to the next question. Does that mean that the Earth might have had rings before? Because we have a moon.
So in the Earth's case, so in Saturn's case, likely the reason that it has rings is because in the same way that the sun, when it formed, pulled a whole bunch of material into a disk, Saturn was big enough that it pulled material into a disk. The Earth really wasn't big enough to capture that much material. It would have potentially captured some, but that's not where the moon would have come from. In the case of the Earth's moon, we believe that there was actually another planet in the solar system early on that collided with the Earth. And the result of that collision was that how the Earth looked changed a little bit, and the fragments off of it mostly became small debris that disappeared, but one big piece of it stayed near the Earth and was captured into orbit, and that's the moon. And a cool thing is that we have really good evidence for this by the fact that we've taken samples from the moon from having gone there, and we know that the chemistry on the moon is consistent, as well as the Earth is consistent with them having formed from the same collision as compared to having formed separately.
Yeah, that's really cool. And it's really cool, that we can be able to do that. We have to measure the chemistry of the moon. Yeah, so then the next question is, what is the proportion of systems that are still forming and have this type of gas disk compared to the fully formed exoplanetary systems?
So that's a really good question. I don't think that I'll be able to answer that with a number. So there's a couple things there. One is all these things we've observed, both for the disks and for the stars that already have planetary systems around them, are really nearby to us in the big scale of how big space is. Unlike some observations, like observations of the cosmic microwave background that we can do super far away, these observations, because of how small these objects are, can only be done on relatively close things. So the first part of it is just that we've surveyed such a small amount of space that it would be hard to generalize it. We don't know if the kind of numbers that we have from these thousands of systems we've looked at nearby is consistent with the millions to billions of things out there. The other thing is all of these searches are very targeted. So we look at larger scale images where we think, there might be stars that we want to look at, and we look at those. So these things tend to cluster in regions, essentially because stars all form together. So we look at one cluster of stars that are all a similar age and all have disks, and another one that don't. But the big picture answer is that there's lots and lots of both of them. And this is an ongoing process. So there's lots of systems that have existed in the past and don't today. There's lots of things that are like the solar system's age, and there's lots of things that are just forming and millions of years old only.
Yeah, a follow-up question on that is, since we can't see all the planets form, we can't see it from the disk all the way to having exoplanetary systems, how are we able to figure out which theories that we have for planet formation are correct?
Yeah, so this is the big question, but effectively, as I motivated, we have some clues from the solar system and these exoplanetary systems that are already formed that any theory needs to be consistent with at least a large sample of those. It needs to be able to explain how the solar system formed, and we know, or is how it is today, and we know very detailed what that looks like. And it needs to be able to explain most of these other planetary systems. There can be some statistical outliers, but it can't fail to explain the majority of them. So effectively, we come up with things that seem to work with this data. And then as more data is created, some of those theories end up not working. And this is just how the science kind of goes in this area. These things take too long to watch the whole thing happen. So we do the best we can to make things work with the data we have, and the number of theories we have goes down as we have more observations.
Yeah, that makes a lot of sense. It's not like, a different type of science where you can do an experiment in a lab. That would be very difficult for something astronomical.
So I will mention that people do actually smash rocks together in a lab to try and imitate how planets form. And actually a decent amount of the sticking together science we know does actually come from labs, which is super cool.
Yeah, that really is really cool. Another question on the detection is, you showed an image where there was all the different sizes and distances to the stars of all these exoplanets. Why are most of them a lot closer to the star and a lot heavier than our Earth?
Right. So when we look at this plot, you'll see that where the solar system things are basically in this region where we have nothing. And so you might ask, is the solar system just weird? And the answer to this is probably not. Basically, all these methods of detecting things. So one of the common ones is the transit method, which is all the green ones. It's looking for a planet crossing in front of the star, for instance, and blocking out some light, basically creating an eclipse. And the closer you are, the more often this eclipse is going to happen, meaning that you're more likely to detect it if you just look for a little bit of time. And then also, the bigger and closer you are, the bigger this dip in brightness is going to be. So if you're really far away or really small, you're basically not going to see it. But something, in the extreme case of another star, it could, immediately there, it could fully block out the light. So we're highly biased in our observations with all these methods, but especially the common ones, transit and radial velocity, which are the two common ones, are very biased to things that are very close to the star or very large. And so a big part of modern instrumentation is we're aiming to push this these observations down and to the right. We want to see lower mass things, and we want to see things at further distances. Because right now our only test case for theories in that region is the solar system, and we'd like to know whether it's consistent with other things in that region.
Yeah, that makes a lot of sense. And you had mentioned that one of these like upcoming experiments is the James Webb Telescope. What are you most looking forward to for what James Webb will be able to see?
Well, so James Webb is kind of similar to Spitzer, but going to have much better spatial resolution. And some of you might have seen recently, they've shown some of the kind of first proper pictures from James Webb compared to other telescopes, and it's much better for what it can see. We'll have to see with time how much we get for these actual disk observations. In the first round of observing, there's not a ton of things looking at these disks. But one really exciting thing from the first round of observation is that a ton of time got allotted to looking at this TRAPPIST-1 planetary system. And people believe that with James Webb, we're actually going to potentially be able to use the spectroscopy method to actually understand some of the constituents of these planets in the TRAPPIST-1 system, as well as get measurements on things like the atmospheric temperatures and confirm whether the things that we think are in a zone that could be habitable are or not. So that's super exciting if you're interested in finding terrestrial planets that might actually be an Earth analog rather than just something like Venus or Mars that's not habitable for us.
What do you look for to figure out if a planet is habitable, or like what are like the main things that you're trying to decide before you try to make one of these telescopes like look at them?
Mm-hmm. Well, so it is still a big question of what does it mean for a planet to actually be habitable? Because the only habitable data point we have is the Earth. So essentially at this point, we try and look for things that have chemical similarity to the Earth. And a big one that's kind of one of the easiest to see because, well, we know on Earth that because we have water on the Earth, there's signatures of water in the atmosphere. Water evaporates and goes into water vapor in the atmosphere. And so looking for water vapor in the atmosphere, as well as trying to calculate whether it's possible for water to be in the water vapor to be in the atmosphere and water to exist on the surface is one of the big things that we do. And that's actually how we define the classical habitable zone, is just, can the planet have water on the surface? With more detailed chemical analysis from these new observations, we'd also hope to be able to look for other things like carbon-containing molecules, things like methane that could be a byproduct of life. We know that things give off things like methane when they live, at least on Earth. And so there's lots of research that goes into kind of which biosignatures on Earth are truly biosignatures versus which we could form by natural mechanisms. But we are actually able to learn a lot about the atmospheric chemistry nowadays, which is really cool.
Yeah, that does sound really cool. And, it sounds like a lot of like interdisciplinary work that can happen between, biologists and astronomers, which is always really cool to be able to do. So one thing that you were just mentioning was the TRAPPIST-1 system, and you had shown that all these planets are super close to its star. How do they not just like fall in or burn up if they're that close to the star?
Mm-hmm. Well, so one thing is this star is a lot smaller. So it's about 10 times smaller than the sun. And so it's a lot less bright. It's a whole different class of star compared to the sun. So they actually aren't that hot compared to the solar system planets. In fact, the kind of middle few planets are in what we'd consider, at least from theory, to be the habitable zone. So we think they could be a comparable temperature to the Earth and have liquid water on them. Now, why they don't just all infall is actually a really good question. A lot of people have studied the dynamics, which is how they interact and move while pulling on each other gravitationally, to try and understand, how do these things actually exist? Because they are incredibly close. And it turns out that that they actually manage to find themselves in a type of configuration that's just very stable. When they get there, they're able to stay stable together, and it's through this process called resonance. And it's hard to explain quickly, but the big idea is if you've ever been on a swing, for instance, you know, if you swing your legs in a specific way, you kind of go higher and higher and it feels really smooth. And then if you swing at the wrong time, it suddenly is going to feel jerky and you're not going to go as high anymore. These planets are just all orbiting relative to each other at just about the right speed, so that they can kind of be trapped in this type of motion where the mutual interactions between them just keeps them in harmony and keeps them from falling into the star. But this is actually an active area of research, and that's a really good question.
Yeah, thank you for that really, like all of your really in-depth answers. They were all really great, and this talk was like really interesting and really informative. So we're going to wrap up for tonight. And yeah, I guess everybody's virtual, but I'll thank Fergus again for this great talk. And I will also thank our volunteers, because without them, this event wouldn't have been able to happen. And also our sponsors for the same reason. And just as a reminder, we will now have a Zoom room where there will be an Ask an Astronomer room and a virtual telescope tour of ALMA that was discussed a little bit in Fergus's talk. And also, please make sure to fill out our feedback form at bit.ly/AstroTours. Thank you, and I hope to see you all next month.
Thank you, everyone.